阳太。
解锁，请启通话筒。
Okay. Last time we talked about some questions that about different Boltzmann law, how it describes the bread body, and the formula about density equal to the sigma t power 4, Stephen Boltzmann law. So because in the graph we have a U versus mu, where U is the energy density. So how we can get from it is basically use the total energy density. Total energy density equal to AT power 4. So we take the integral from that energy density. We take the integral from the, let's say we have a Planck distribution. This one is a Planck distribution. We can take the integral from 0 to infinity to recover the Stephen Boltzmann law. So the idea is that it describing the Stephen Boltzmann law from the start. And one of it is the idea that they discover this formula from thermodynamics and also the empirical data that they try to fit the formula. And this one is A equal to 4 over C sigma is by the argument of the kinetic theory, which one, this one I put a question mark here, so this one I'm not sure yet. Basically, it can transform from I to total energy density. And yeah, total energy density. And from a Planck distribution, we can take the integral and get back the formula for Stephen Boltzmann law. Yeah. So the main point is that the exact form of the Stephen Boltzmann constant, which if argued from the classical mechanics, it cannot be determined. The sigma then. So it only until the Planck distribution, the realization of the quantize of energy, and also first introduce of the hash here, the Planck constant, and it recovered when it recovered the Stephen Boltzmann law, the sigma here is appear in this form. So yeah, this one is getting from the Planck distribution when we take an integral. And sometimes we were using the reduced Planck constant, which is in bar hash equal to hash over 2 pi. Yeah, this one I would like to answer in this way to solve the problem.
So which equation comes first?
Which equation comes first? I equal to sigma t power. And then it first comes with the empirical formula, which is to fit the data. And theoretically, it verified by Boltzmann through thermodynamics. And
You mean this I equals to sigma.
yeah. And also the sigma, but the sigma here is just a concept. We cannot determine what is it.
I think you should write sigma.
Okay.
And then why you define your total energy density as actually just a multiple of this I.
Yeah, multiple of
4 over C.
I equal to 4 over
C is
C.
big of light.
Yeah, speed of light. C is speed
So
of light.
why total energy density is defined as such?
Why total energy density is defined as, you mean this one?
Yeah.
Initially is come from this relation, and when we substitute back to,
So where does
we'll get this one. This one will come from a kinetic theory here.
So
Which
what is I again?
I is intensity.
Density of what?
intensity of a source of a light. The radiation that emitted by the body.
So what's the unit for I?
Intensity is power per area, which is dE over dt over area. This one is total energy density, so it's E over V. This one C is meter per second. Meter per second.
Yeah.
V E is energy, total energy. V is the volume. How you get the area from?
In another dimension.
Because C here is let's say this meter per second, so it's cancelled out with so this will be area.
Ah,
Yeah, it's calling from this dimension.
what over one I equal to
1/4 C.
what is that one? N.
Oh, this one will be the kinetic theory that I search is the come of the idea of number of particles. Number of particles at unit area per unit time is 1 over n is the number density, sorry. Number of particle per volume.
What's bracket B?
Bracket B is the mean speed here.
Yeah, I think a good practice is whenever you write down these variables, make sure you write what are they.
Okay.
If you read the textbook, right, you'll see they will write where I is large, not equal to T. So
Oh,
yeah, otherwise, I'm not sure what you are talking about.
okay.
Okay. And then why you mention H bar?
Oh, H bar just for our afterwards, maybe we will use this Planck constant, reduce
So you mean H is the first constant appear here.
yeah, in the Planck distribution yeah, coming from here. The quantize of energy, quantize of energy.
Why the integral of U is epsilon then?
Integral of mean this one.
Yes.
Sorry.
Yeah, why is it defined such?
On this one, because this one is the energy density for the specific temperature and also the specific frequency. So we equal this because we
So you mean UVT is the total energy density at a given time and what's the density?
U is not E is total. The U here is not total. So
It's just
yeah, energy density. So we want to sum up all the possible frequency. So we take the integral that is ranging from 0 to infinity.
So how do you measure U again?
How do I measure U again? How do I measure U?
You said from experiment, right?
Yeah, it's from an experiment.
Yeah. So
Intensity I know, but U I'm not quite sure is how to measure. Yeah.
because you say from experiment, right? So I think you need to figure out otherwise how you record the data.
And maybe the intensity is from the experiment and the U is from the theoretical experiment, they're plotting the graph. Let's say E, because the intensity we can measure through the apparatus. Let's say there is a light, there is the there's the apparatus that can detect the light. Then it can convert into the intensity values. So I think that one will be measuring the experiment that measuring. So the U here, I think that is from the theoretical perspective that they never using U.
I mean, how you obtain?
How I obtain U. For experimentally, I'm not sure.
Not internet.
So, so far, I really am not. So far,
They try and find out.
can.
Isn't this kind of question not interest you?
This measurement thing.
You don't care? I told you are physicists. Physicists should know. I mean, you are theoretical, obviously, but
Yeah.
I mean, theoretical come from experimental.
Mm.
You don't have experimental, how you prove your theory.
For me, practical things that I not quite like. So, I mean,
I mean, you can not like it, but
Yeah.
I don't think you cannot.
okay. So,
Understand what I
yeah,
said?
yeah.
Yeah. Otherwise, how? I mean, this is a logic gap. I mean, knowledge gap.
Mm.
If you don't know thing, don't even know how to measure thing, then how to do? Who can believe you?
Okay.
Accessible.
Right.
Yeah. If you don't even know what your theory are talking about, then why makes sense? For example, like Einstein before they come out with relativity, they also come out with the experiment, right? The photon electric,
The relativity.
yeah, before relativity, right? And then after he do this experiment, and then he come out with this idea, right? Yeah, right?
Photoelectric effect is quantum mechanics, but relativity is other thing.
I mean, isn't it that give him the idea to develop?
Maybe.
Yeah, I mean, the point is like you at least need to know. At least need to know how the basic work out. This is my point.
Okay.
Yeah.
Okay.
I mean, this is the some basic you also need to. Sometimes the book won't write these things down because maybe sometimes seems quite trivial or maybe not quite related. But now, if you want to do a proper researcher, do a scientist, then these basic question actually you need to ask yourself. Yeah.
Move to the next one. The question, second question, yeah, that I consult Professor Thomas. Why we cannot accumulate? The question is like, why we cannot accumulate the energy with the wave, sorry, with a light that is lower than threshold frequency to get the photoelectric effect done. So this one I talked to you about the potential well, which is not properly introduced yet. As we can get the idea after quantum mechanics, but Professor Thomas mentioned that maybe the photon, the light that collecting the electron, because this metal surface, like a metal surface have a many electron and also atom. When it's collecting the electron, the energy it disappear to the surrounding, which is causing it in a vibration. So in a sense that energy is conserved, but the energy is still not enough for it to come out from the metal. But he also mentioned that maybe if there is a real case that two photon add up together, the two photon have the total energy that is bigger than the energy that's needed for the electron to come out, then this will be the case. Maybe electron will come out. Yeah. Okay, so there is a real case. Perhaps the electron will come out if two photons collecting the electron together and transferring the energy into the electron, which is higher than the energy needed for it. Then yeah, this will be the case when the two photons collide the electron. Maybe
So you mean the two photon?
maybe two photons having the total energy that is bigger than the we call it work function, the energy needed for electron to come out from matter. So
But
that is a little
These
different.
two photon don't have the threshold,
Yeah, don't exceed the threshold.
but we still get achieve photon.
Yeah, if we two simultaneously collide each other.
So actually it's really energy problem. So can I think of like can I think of it like it's a one-off thing? So as long as you keep the energy, then you can come out.
Yeah. So
So if you continuously, then it's not like a switch. Okay, I think we should think of it like a switch instead of like pouring the water.
yeah, sheets. Because we pour in the water, the energy will disappear to the surrounding of the electron and also the atom because it's
So
crossing.
are you talking about proper theory now? Or you are just thinking? Is this a proper theory got already?
Proper theory,
Yeah.
you can get the idea because it's also coming from Professor Thomas. I also give me some idea.
I mean, is it like properly like tested or what?
I think
What theory is that?
solid in the solid state physics, that is because electron and also atom having the binding energy, right? So when we collide the electron, will because it's binding to a bind means that is associated to it.
I know.
Okay. So it's like the field, when there's an electron transferring energy will cause other electron and also surrounding nucleus. I mean, in general, it's atoms will get the energy to vibrate also. Yeah, that the energy that disappear to surrounding is very fast in the sense that if two photons to in the sense that if the electron to accumulate energy is kind of impossible for it to accumulate so that the electron will come out.
So you mentioned it's a solid state.
Solid state physics. As a branch of theory, because I mentioning is a general one, but I think there will be theory that is very keen.
What about you hit it fast enough?
Perhaps it can be done if two photon is hitting the electron simultaneously.
I mean, close to simultaneously.
Close to simultaneously.
Right, okay. So the thing I imagined was you hit, okay, dissipated, right? Then hit, dissipated. Let's say you hit it again before the previous energy get dissipated. Can I still get photon energy? Okay, maybe this is an open question. You don't need to answer also can, but I just give an idea.
Maybe it's small amounts of.
You mean the dissipation is instantly?
Dissipation Special not, but it's very, very short time. It's like,
I can shorter, I can make it shorter and shorter.
very short. I don't have an idea of like, increase the, it means like increase the intensity of photon so that it can, yeah, I get an idea, but, so how, so I'm not sure is it. Whereas the time, the dissipating is quite significantly smaller than what you want to do. I think because the electron have the limit of speed. The photon is going with the speed of light.
No, I think the difference is our control, right? So you can shoot one first and then shoot one later. No.
Usually we shoot the whole branch of the photon because it's light there.
Then what do you mean by two photon hit at one? Then how do you make it?
This because a whole bunch of photon, maybe two photon that is possible to hit simultaneously.
Then previously, how you achieve one by one?
You see achieve the ideal case of when the photon hit it, yeah, this one photon hit the electron of this ideal case, but the whole bunch of others may not be achieved of photoelectric effect. For example, yeah, okay, because the photon, and we are talking about photon and electron, maybe there is a case that the photon is not hitting electron elastically. Elastically, that's transferring all the energy to the, I mean, the energy is conserved. So when we are talking here is the ideal case that the photon energy is all of the photon energy transferred to the electron, which let the electron come up from matter and having the maximum kinetic energy. So maybe whereas in the real case, the energy is disappear some way. It's not, maybe it's not elastically.
No, I know how you shoot a photon like that.
Mhm.
So when you shoot it, do you shoot it one by one or you shoot it in a bunch?
In a bunch,
In a bunch.
in experiment.
Okay, and then the theory, why they explain it as one by one?
Theory is because it tends to simplify something. I mean,
Even if you want to simplify, it should like
there is
reflect the real life.
yeah, there is an uncertainty there of the data. There is maybe during the experiment we have an uncertainty of the data because this is a theory. This is an ideal case. When we do experiment, we not, maybe for example from the graph we are not getting whole straight line. Maybe get this get other point as well.
Why suddenly there's something to do with it?
I introducing the idea of uncertainty in the experiment. So the uncertainty that deviates from the theory, which I think in experiment also we accept certain range of uncertainty. So we are using the standard deviation if the experiment is falling, let's say in the range of this.
So you mean the experiment data is not suggesting the photon is hitting one?
Yeah, maybe it's not colliding one by one. Maybe it can be like we mentioned, the two photons collide each other, they collide electron at the same time.
Then how you so it is the threshold frequency.
How we can conclude it's a threshold frequency? when we fall into the range of the standard deviation of yeah, when the data is falling into the standard deviation from the theory. Again, can you come again?
Just now you said that, okay, previously you said that this photoelectric effect explained that photon transmit energy in a briquette, right? So that's why we have quantum. Okay, so it is hitting one by one to this electron, so transmitting wave packet or energy packet, right? Okay, and then once the energy packet hit the threshold frequency, then this electron will jump out. Okay, and then I ask a question. Because energy is equal to HV, right? Okay. Let's say we don't provide the enough frequency. Okay, but the threshold frequency also define the energy needed to do the photoelectric effect.
You mean
The threshold frequency will define the energy needed because H equal to HV.
yeah, the energy needed, but we are using work function for the. It's another term. Work function that is qualitative. I think it's qualitative. Describe the energy needed. Yeah, energy needed. Okay, something like that. So it's yeah, it's related, but it's not directly equal.
VH not equal to, I mean, you mean E not equal to HV?
Because you are suggesting that energy of the electron is E equal to H mu this.
So I mean, like if okay, so the conclusion is if you hit with threshold energy, then you will get the electron.
Yeah.
Is right.
Yeah.
Anyway, so I mean, E equal to HV is correct.
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 For photon.
For photon.
Because we.
Yeah, okay, that's fine. And then so with the threshold frequency that can admit the electron, and calculate the energy.
Calculate the energy of a photon.
Yeah.
Okay. Yeah.
Okay. So now I don't provide the threshold frequency. Instead, I provide energy. So I make my frequency lower. But you said that maybe we have a chance to like simultaneously hit the electron. Then you said that it's possible that we also can hit electron in that case, right? We also can have photoelectric. Right?
My idea is, yeah, we not providing the enough threshold frequency, which is the energy is not
Okay,
enough.
let's call that E to be threshold energy.
Yeah, okay.
So I give it enough threshold energy instead.
Sorry, you give
So I
enough.
provide electron enough threshold energy.
Mm.
And then I obtain this threshold energy from the threshold frequency.
Okay, yeah.
Make sense, right?
Okay, yeah.
Okay. So you say also can emit, also can have photoelectric effect. So my problem is, so how do you make sure you hit the electron? I mean, yeah, hit the electron with one photon at once or simultaneously with photon. How do you do that? But you say that we can always shoot a bunch of photons and
In reality, we only can shoot a bunch of electrons.
in that case, then how they come up with this one by one shooting?
How they come up with a one by one shooting?
The theory is one by one, right?
Yeah.
So how they use this to verify? Yeah, so.
That's why I bring out the experiment uncertainty.
You understand my question?
Yeah, I get it. I get it. I think the idea is they verify the linearity from maybe you have a whole bunch of data when you're plotting a graph. Then you can plot a linear graph of the energy versus the mu here. Is that answer?
Or you repeat my question? I will repeat my question.
Your question is why the theory is about one by one, but we are doing the whole bunch of the photon. In reality, we cannot control one by one photon. But it's simplify the case, we use a one by one photon to do the experiment. Sorry, to not do the experiment, do the theory.
So how significant?
When you get the data is the linear graph, the versus E versus mu. So, which means that if confirm the linearity from the theory,
How the theory is shooting up by one kilometer? What's the relation between it?
what is the relation between energy, E, E? We are
This linearity suggests
okay, yeah. How did get what? I'm thinking is it most of the case will because you have sorry, the photon is hitting one by one, and some rare cases is not it's not hitting one by sorry, what I say.
If like that, then how can you call your theory a theory? I thought this is just shitting.
Pushy.
Shit. I also can push it something else. You understand or not?
Yeah.
So, but if you call something a theory, it should work at least for most of the cases. You know, say some of the cases. Then I also can say my theory work for some of the cases.
Yeah. Maybe I should also this maybe this one is a simplified version that is to to get the idea. To give the idea that is because we considering the ideal case of proton collecting electron one by one, and it's not matching with the wave theory.
No. My problem is, so who come up with this idea? Einstein.
You mean the theory?
Yeah.
Einstein.
Can you read the original Einstein?
And yeah.
It's the paper he get the Nobel Prize.
Can
you read it?
Okay. I have it in Evelyn. Yeah. I think it come up with I just go through now he go through the arguments of the total habits and he introduce the idea of it, but I will go through it again. Yes.
I think those like really simple.
Okay.
Like the case where
Mm.
they are doing the theory, looking at the one by one is easier. But experimentally, you cannot do that. But you can approximate it in an epsilon error.
It's an error of uncertainty. I mean, it's uncertainty that in the data.
Yeah, so that's why your theory works, right?
Autoprovable is I want you to explain like why 1 to 1 will give rise to this so-called ideal linear line.
1 to 1 give the idea of
Yeah,
linear.
1 to 1 transmitting process to give you this idea.
Oh,
You ever make connection between this? You just said that I assume a 1 by 1 transmitting of photon, then I will get this linear line. So why?
this one I can explain now. Is from the formula is energy of conservation. The photon energy at the left hand side transmit to the electron have a work function, and also when it come up have a kinetic energy. So when we're writing down is h mu equal to W plus K max here. The K maximum is the kinetic energy, which is again half me v squared, and the work function for W. Yeah. And the K maximum kinetic energy maximum here can be done from the experiment that you apply the potential, the reverse direction of the potential. Because electron, let's say we have a whole bunch of electron that coming out. Some of them will have a maximum kinetic energy, okay, that can come to the anode. So this will give rise a certain potential. Okay, so we apply the reverse potential in the reverse directions to make the electron, all the electron, including the electron, have the maximum kinetic energy to not arrive in the anode here. So this potential we call it Vs, and times with energy, times with E charge of electron will give us the energy of maximum kinetic energy of electron. So we can plot the graph just equal the inertial one is EVS H mu minus RP. So we are plotting a graph Y versus X, the linear graph here. Yeah, this is why the linear graph come from the formula. The okay.
That's the simple. You have to ask yourself, okay.
I think okay.
You think okay? You think okay?
Yeah.
You think okay? Let me think.
Okay.
So you mean you arrived from this equation if you assume there's just one energy that can. So the conservation of one conservation of energy of one electron in the and then this theory will approximate the experimental data.
Hmm.
I think you're only using one V, right? Actually, it's not quite sure how you get this V. Maybe he associate one V to one photon. You understand what I'm saying?
You mean about V potential? The frequency?
Yeah.
Uh. Okay. Mean,
I mean, the explanation of this V could be different. It might not be one electron, one photon giving this.
yeah.
Or this HV maybe can change also. Like what you say, if I gave 2 electrons, then give enough HV also. My problem is we don't really see how the electron, how the photon give you this HV, correct or not? Because my step is like what you say, I give a bunch of photons to it. So why my idea, maybe you can read the paper again. My idea is maybe when you think about this equation, right? Because there's only single V appear here. So maybe it's natural to associate this V to
Different
one thing. And then he called that thing quantum photon package. You understand?
Yeah.
So how to achieve this V, who knows?
Whole bunch of photon, because we can control the wavelength of a light, which is the frequency of a light. So maybe there is some discrepancy of the photon that is not associated to the V that you want. If it's I can guarantee that most of the photon is having the energy HV. Then yeah, just we hope most of it will be follow this straight line. If other maybe the photon is not following this energy of H nu, maybe the data is discrepant from the straight line here. So yeah, that's why I have uncertainty in real life. Okay. I'm not sure we are too focusing on there's a question you asked also about I'm not sure we are too focusing on the experiment, but we are not going to the real quantum mechanics, because now is the times already. So following my thing, I want to introduce the quantum mechanics in the formalism and also like that. Yeah, this one I try to answer you when we are meeting during class or after class.
Which one?
The possible question that I bring out, the question that I bring out just now. This
You can answer it actually inside your note also. You can answer it into your note.
okay.
Yeah. Then just include it inside the note.
Okay. Because I answer this in the notes also. The Compton scattering, why the graph is behave like this. Should I? You asked about Compton scattering, how we can do the experiment to measure. Should I answer now? Short question. Should I answer? The graph we getting is to hit here. To answer. We fix the theta. We fix the theta angle here. And measuring the intensity, because yeah, it's still the Compton scattering formula that I introduced you is the ideal case when when it when when photon hit the electron elastically, same as like the just now the ideal case, but in real life, it might not collide the electron elastically. So having some others like discrepancy from the theory. So the idea we are getting these two peak here. One of the peak is matched with the quantum scattering that predicting the wavelength. This right hand side here is about quantum scattering. The left hand side is what is done is when you consider the electron is strongly bound on the atom, because electron we are considered is free electron. How I can show the electron is through the metal surface, and we are assuming the outer surface of the electron, a certain kind of the material, have the very low energy, and the photon that hitting it is very high energy, so we can consider approximate the electron as a free electron. But there is other electron that is tightly bound to the nucleus. And when you hit that, when the electron that is hitting that electron that is tightly bound, whole atom will be scattered. And when the whole atom will be scattered, the change of the wavelength, when we substitute the formula into the quantum scattering, we are considering the whole mass of atom. The mass there is in the denominator terms. The mass is very high, so we get a result of a delta lambda. The change of a wavelength is very small, so that's why we have a second peak at the left hand side. When there is a case of electron is tightly bound to the nucleus. Yeah.
So you just said that one is tightly bound, one is free. So this is the short answer.
Sorry. Short answer. I forgot.
What?
Yeah, I
what
mean,
I say is correct or not? One
yeah,
is-
correct.
So this is the short answer, right?
Yeah, I forgot what to show the short answer. Okay. Yeah. The diplomatic wavelength is not, I still don't know why. Maybe that's kind of the symmetric sense is, because it's a photon is a kind of material. So we considering all the other materials inside to this hypothesis. I don't think this answer will satisfy you. But I still cannot solve this why generalizing that in his PhD thesis. Perhaps we can, yeah, that's right. Because we are saying hypothesis, we just propose it, but
Media will link you to the right reference.
original paper. Yeah, this one I haven't come up with the satisfying answer. But maybe this one I want to introduce also in today talk. Is explaining the Bohr atomic model. Bohr atomic model. So we come with the first discovery of the atomic model proposed by Rutherford. Rutherford is get the idea of when the Earth and the other planets surrounding the sun. So he thinks that maybe the nucleus, which he found the nucleus from his previous experiment, is surrounded by the electrons. So you can get this is a surrounding the atomic model, Rutherford atomic model. And the problems, there are two problems. This first one is the atoms are unstable. Unstable in the sense that when you think the electron is surrounding the nucleus, the electron is accelerating. Okay? The accelerating electron will emit the electromagnetic wave.
From this picture, I cannot see the acceleration.
Maybe it's from here.
How should I see?
The electron is because its electron is going to the in its model, electron should go in orbital motion with the nucleus, but electron is accelerating. So electron is accelerating from the Maxwell equation. It will radiate out the energy in a form of electromagnetic wave. So when the energy is decreasing, it will eventually orbit very near, comes near to the nucleus and fall and collide to the nucleus. So this is a problem that from the Maxwell equations, the EM theory, is the first problem. The second problem is it cannot describe the atomic spectrum.
But you say
Oh.
it fall into the nuclear part, then why you draw it like that? Why you draw orbiting around?
This is the model he proposed.
So because of this problem, so he was this.
No,
This model or this problem?
yeah, this model got this problem.
So I mean, you didn't draw the electron moving. Why orbiting faster?
He proposed the model, but doesn't consider the problems of he doesn't consider problems of these two problems are
So which one comes first? Model comes first or problem?
model.
Model comes first.
Hence, after that, the people realize it doesn't match with EM theory.
So Maxwell equation comes after this model
No, it's before that.
or before that?
It's very long ago.
Maxwell equation is in 19th century, right?
Yeah, 19.
Maybe too humble, no one reads. Oh, yeah, until this.
Yeah, I think he proposed this new model because because there is a model that is the atom is a collection of electron, no nucleus. So he proposed this new model, although didn't it didn't match with the order theory. He want to propose there is a nucleus inside it. He didn't manage to answer the previous theory. Okay, the second one that is the atomic spectra. When the atomic spectra, the spectrum of light, there is a discrete line, discrete lines in between the spectrum. So yeah, the atomic spectra. Okay, so they are trying to explain why they have a atomic spectrum. When the electron is emitting the wave, EM wave, it should be emitting in a continuous spectrum. Because the energy that come out, yeah, is continuous spectrum. So because the frequency of the radiating energy is decreasing, and also, sorry, bring again. Yeah, this idea, the EM should be predicting that it should be the continuous spectrum. Yeah, these will be two problems that cannot explain by the Rutherford model.
So cannot describe the atomic spectrum because some of the lines is missing.
Cannot because it's discrete. Yeah, it's some of the line is discrete. For example, the spectrum should be from red to ultraviolet, for example. But there is the dark line there. which they cannot explain in between the
Okay,
spectrum.
one thing on this explanation. So I guess because you're bringing up new wood, right? So make sure you define this word properly first. So you produce properly what is the atomic spectra, and then how this model will give some form of atomic spectra, and then you try to say that these two atomic spectra is different, right? What did it like?
Do not explain because from the experiment they found there is a discrete lines, but this new model cannot explain why there is a discrete line.
So what this model can explain?
The nucleus, only the nucleus, I think is the important part. We want to introduce a next model, which is more the new model, just because it's just a previous of the low atomic model. So these two problems can be explained by the low atomic model, which I will introduce.
Actually, yeah, I think there's some problem.
Ah.
Is this the way how textbook, physics textbook say? The way how physics textbook expresses it? How they mention there's a problem with this butterfly model.
I simplify it. I mean,
You simplify it. Because when you simplify it, there's something missing. When I hear your presentation, there's something missing. You can go back and read again.
okay,
Okay, now I predict what something is missing.
okay,
So you are missing how this model will produce atomic spectrum. Okay, otherwise you cannot say that it cannot describe.
this atomic model didn't provide the spectrum. I mean, the experiment and the model.
If you cannot describe, then what for come out with this model? No point, you know.
Because he realized that,
Naive already. Too naive. Not like that.
okay,
If you cannot explain something, why people will take this theory? It should have some explanation, but that explanation is not good.
yeah, the model he introduced because he found the nucleus.
No, too naive.
Too naive.
You sure missing something one. You go back and read again. Too naive. You cannot. If like that, I also can simply come up with a theory. Never mind lah. This one cannot explain this, but please take it. Cannot like that. This one is too naive. This thinking is too naive. Cannot.
Okay.
The scientist is not that simple one. You understand?
Yeah.
It should give some form of. You go back and read. Make sure you go back and read. That for sure there's something you're missing. It's not as naive as you think. It should give some explanation, but that explanation is not. Okay. You understand?
Mm.
Yeah, try and go back and read. Otherwise, they don't need to mention this thing. Useless. If there's something, okay, you think about simple logic. Simple logic. If there's something that cannot explain this thing, then why they accept this as a theory?
No, it's not a accepted theory now.
I mean, at that time, it's accepted before. Otherwise, why people bring it up? For sure, it's accepted for some time, and then people realize there's some problem. Right about.
Because they found nucleus. Because they found nucleus.
No, I mean the way you explain. The way you explain this atomic spectra. I mean, how to say?
Yeah, I can better because I didn't include the things.
What thing?
I mean, I didn't explain why it's an atomic spectrum.
Let's see how I explain to you this.这有一点像欲加之罪，你知道吗？
什么？
你懂？一家
你说中
欲加之罪你听不懂，就是你没有做的事哦，我偏偏讲你做了。
OK，我没有讲解。
OK， First problem is you haven't really explained this model well actually. You just draw something out. Actually, I don't know what this drawing is.
Okay.
You understand? I also see this picture before lah in my high school. That's it. But I didn't really know what it is actually. 不知道，我不知道。我怎么来了？以前画家又怎样？
Okay.
不知道。So 我在不知道这个情况下，你又跟我讲这个东西有 problem 啊？莫名其妙诶，你知道吗？
Maybe the point that I didn't explain well the other four
啊，
model.
对。I mean, picture can be simple, but when you explain it, you cannot just say look at the picture.
Okay.
因为我 look at picture，每个人可以看图说故事讲不一样，100个故事都可以讲出来的，你明白吗？So
Okay.
you need to really define it well.
Okay.
OK， 这个是第一个问题啊，我不懂这个东西，然后你又跟我讲这个东西有问题，我是不能够 verify 这个问题的。
Okay. Okay.
OK，
Okay.
Yeah.
Yeah. Okay.
也，对吧？
嗯
这个是诈骗的由来，诈骗就是这样开始的。跟你讲一个你不懂的东西，你做不了，就是你做的，OK，我做的我还钱就好了，解决掉了，这就是诈骗了。
Okay. Then I can explain a bit how it come out with the nucleus in the middle.
No need. I also know that. What I know, what I wanted to know is really the recipe for this movie.
Yes.
Yeah. The nucleus, I also heard it before, right? It's like shooting a photo and then hit something inside there.
Shooting at your
The photo is away, right? Something. This one I also know. Right? The problem is I want to know the recipe.
Okay.
I don't know the real recipe how
Yeah.
to construct this picture from scratch. 什么都没有的把它画出来。
Okay. Okay.
And then 才 bring out 这个 problem.
I'm not sure this for us should be really investigate this all quantum theory because I mean
不是，这个不是关于你要不要 investigate 不 investigate，这是你不懂。
the focus
这是
point
knowledge gap， 这是 gap。你要 explain 不要 explain 都不用紧，但是现在是你不会，这是重点。你要讲不要讲是一个问题，现在问题是你不会，不会是个大问题。你要讲不要讲是另外一个问题，
okay.
有差别。
Because like how the experiment done, it should be experimental physicists that done
我没有讲 experiment， 那我现在在问你 theory 啊，讲话出来啊。
theory 讲话出来。
哦，对啊，不是讲话出来。我现在在问 theory 一个问题，我不是在问你 experiment 的问题啊。我 experiment 也会啊，我拿那个什么出来产出来嘛，里面有东西哦，因为它产出来东西。
Yes.
对吗
Yeah.
？But 为什么想到这个东西 ？OK， 你有一个东西讲了 ，and inspired by 这个 orbital motion OK 了。But and then 但是 like 你不能够讲我 inspire 我就想出来这个 theory， 我还是要 verify 这个 theory 吗？你都没有做一个 verification。你看你刚才在 explain 另外一个 theory 的时候也没有 verification 了，你就相信不了，你就相信人家跟你讲的东西，就这样，这个是一个很大的问题。
Okay.
人家跟你讲了一个东西，你要去 verify 的。
要
用什么 verify？ 你自己要找出来哦。One time is experimental. I mean, almost every time 都是 experimental 啊，其实 for 你们的话。Yeah. 然后就 like，yeah，讲或不讲 ，OK， 那个是一个问题，不会那是另外一个问题。
Okay.
明白吗？
Okay. 有太多细节，我想去了解的。
对，我知道很多细节要你了解，但是就是说，没办法，呀，就算你没办法。我跟你讲哦，你这个 gap 哦，以后会变成一个很大的问题啊，它会在你的 research 上面变成一个绊脚石的，就是因为你不会这个东西。
OK，
你就是挡在那里。
OK，Okay, I go back in English again. Okay. The Rutherford, after the Rutherford model, the Bohr atomic model he proposed, he combines Rutherford model and the prime quantum hypothesis is E equal to h nu, that quantization of energy, the idea, and also the photon concept for derived from Einstein. He proposed a model with some assumptions. I just just doing some assumptions. The assumptions of the Bohr atomic model is the energy level is in a discrete set of circular stable orbits, which the stationary states we will explain. No, the stable orbits also we call it as the stationary states. Like energy levels is that for electron will be allowed is only in the discrete energy level, which I draw in a circle here. And this one is a nucleus. This is the first assumption. And on the second assumption, the orbit. Okay.
有没有注意到你又 repeat 的 point？
对。
在讲练第一排字的时候，然后你又跑一句画出那个圆圈，你在讲两句同样的东西，你有发现吗？你如果没有发现，你回去听。
OK。Just one.
我要你意识到你在 repeat。
Yeah.
OK， 你可以有想，I mean 你可以有讲，你可以有意识的，I mean 不是。你可以想要 repeat 它，但是我要知道你自己是在 repeat 着它，我不要你在不知道的情况下一直在讲同样的东西。
OK，
我
get 到你讲，
你懂我讲过吗？
呀，
你懂我讲过吗？
呀，
因为你讲第一句话的时候，那个图片在我脑里面了。
也很不自觉就。
对，你不自觉，所以我就说你一定要知道你自己在做什么，有时候。OK， 你可以。很有意，I mean， 你可以讲啊，突然间那个字忘记去。你可以要做这件事情，但是我是你要自主的知道要做这件事情，而不是在不自主的情况下把它做出来。
OK，
明白吗？这样啊，不然的话就好像在念咒语那样。
Yeah, second one, the allowed orbits corresponding to the orbital angular momentum is L equal to NH bar, where the N is taking as integer number from 1 and goes on. L here is the orbital angular momentum, and the H bar we introduce is the reduced Planck constant, which we call it also the Bohr quantization rule of the angular momentum. And the third one is when electron want to transit or go to another energy level, it only can emit in the form of discrete energy level, discrete energy, which is equal to h nu, radiate or absorbing the energy. Here we will derive the formula is associating for this Bohr atomic model. Suppose we have the simplest model is a hydrogen atom, the proton and also the electron. And from the Newton's second law, F equal to ma, the electron will experiencing a electrostatic force, which will be pulled by the proton. But the proton is very high mass compared to the mass of the electron. So we can assume that the proton is not moving while the electron is orbiting around it. And here we will the F equal to ma, centripetal force, and also the A here is the centripetal acceleration. The only force is experienced by the electron is the electrostatic force. And we can change the MA equal to MV squared over R. And after some algebra, we'll get, arrangement, we'll get the radius of,
What's the left-hand side? Electrostatic force.
yeah, electrostatic force. Yeah, electrostatic force, and after we arrange and using the rules that proposed by the ball, we will get the allowed radius of the electron is in this form, which we see that there's an n here associated to the quantized discrete energy level. Yeah. And the front terms, the whole chunk there, we call it as the N naught is equal to ball radius. Similarly, from the equation before, we can get the velocity of electron orbiting around here in our case is proton. The velocity is in this form. And the main point is about the allowed energy level. Allowed energy level, we can start from energy, the electron that have electron. So when the electron is moving around the proton, it has kinetic energy and also the electrostatic potential energy that is associated to that electron. And also we will get the energy of the discrete energy for that associated energy level is in term form. It's a bit okay. So if you draw out the energy level based on the equation just now, the En and something to 1 over n squared, you can get this energy level, this energy level until the E infinity, we define it as equal to 0. Okay, because you're taking, it's not defining, but when you're taking a very, very large value, the En is approaching to 0. And there's different series which comes before ball atomic model. 3 of them is Lyman series, Balmer series, as Paschen series. Let me explain. Lyman series is when the other energy level fall into the energy level n equal to 1. Let me rephrase it again. Lyman, Balmer, Paschen, they found this empirical formula. Yeah, this come before the energy level realization of the discrete energy level, Lyman series, Balmer, Paschen. And the point is that they found it through experiment, not from the theory. Which the experiment that we talking about just now, the atomic spectra, the discrete lines, it appears in the experiment. So in this more atomic model, it solves the atomic spectra problem because the electron can be radiate the energy, and when the electron is absorbing discrete range of discrete energy, so the spectra will have a dark line there because that line of the photon, is absorbed by the electron, so it will be a dark line in the atomic spectrum.
So how to see from this series?
You can see from the formula.
What's the use of that series? Is that the series will solve the problem? Or how is it solved?
The series is found from the experiment. Yeah, Lyman series, Gamma series, and partial series.
Yeah, how to solve the problem.
How to solve a problem? It's not not this solving the problem. The problem is from the discrete energy level that is the formula that we found just now solving the problem.
Why you bring out this?
To mention in before the model is already experimentally we found it is a result. Yeah, and the point I want to mention about when you have
Wait, back this.
Yeah.
那我在问什么？
为什么这 series 要被介绍？因为 because maybe it's one thing because it's experimentally found and from the model we can verify the experiment. This experiment.
You got this series, and then the EN computer give you the horizontal line. Okay. And then
Explaining why the series will
this arrow. Green.
太在了。That's all stereographic projection.
I think I
this 我知道，我是这样说的，我不是讲说。我自己讨厌我老师的，因为我会不会。我以前做那个应用题啊、数学啊，不知道怎么做，他叫我算几个，真的，我知道他叫我算几个电灯杆，我不会算，我一直算，一直少，
很难
算到2秒，算一
那个
个，
transformer 是吧？
然后我一直问我爸不要跟我讲，我就哭。
你做negative 的那个 energy，
等他算出来我们
没有啊，因为它是这个，我按照我的理解，这个它的具体数值是没有意义的，你可以随便取一个地方为一个 zero，它这个地方就是取了跟你的不是 zero，一个就是 zero。
那这个能量代表啥？就是第一个 orbit 的能量。
看到 potential，
可能 Lyman series 跟其他 series，我觉得我再找一次的这来 investigate，because previously 他们的 experiment 应该没有出现这个 series I mean 这几条线，这几条线是 after more atomic model is introduced and it come out with this formula and we plotting out the formula of En versus N. The horizontal line means meaning of the horizontal line is the energy level there is different. Yeah, the first orbit and the second orbit and the third orbit and etc. You will find that because N is getting higher, the energy gap will become smaller. So eventually at the N is very large. If we approximate to approach to a value sum. So approach to a value and equal to the 0. And after the energy, I want to give you the idea of we will found a discrete spectrum with if the electron is in the bound state to the proton when the energy is less than 0, you'll find the continuous spectrum of energy level because the electron now is free from the proton already. So now the electron can freely move and freely have the continuous of kinetic energy. So the idea of continuous spectrum, unbound state.
也是这样多都没有用，就是没有解决到那个解释的问题。
这个过后再
对，你可以过后，你可以过后，但是我是说过后你在读东西的时候，就一直跟你讲，先把它 connection 读出来，你不要告诉我一大堆理由。我要 connection，先说服你自己先，你觉得你被你自己教的东西说服我应该要 convince 你，不要被你平时所以就说不明白，就是不明白，我不能够看到他怎样能够解决这个 dispute 不 dispute 的问题，我不明白，不明白。
怎样解决 discrete 的？
你有看过？I mean 你都读这么多书啊，你差不多几岁啊你
24。
？24
啊。
你在班上有没有听课？听老师教的东西？
certain only。
的东西
是啊。
OK，so 如果你有听课的话，有几种老师的存在了啊，一种老师就是会告诉你的，就是 step by step 告诉你看。
啊。
那还有一个老师哦，他会讲到你不明白的那种。
诶，
对，
有一个老师，
会讲到很明白。
嗯，
为什么？因为他会告诉你这些 step by step 后面到底发生了什么事情。
诶
你明白吗？
，OK，
所以你再重复问你自己 ，OK， 我给了这个 explanation， 我满意吗？你自己满意？你看我盯着啊，我盯着那几条线看啊 ，OK， 怎样联想到上面那个字？盯着那几条线看啊，我只要联想到后面这个字，要解决刚才不能解决的问题。你看又回到一个问题啊，我连那个 atomic spectrum 都不是很懂的情况下，又要解决这个问题
啊，
明白了。So， 你都来上我的课上了4个星期了。
3次差不多。
对，我每一堂课我一定先把这个字眼讲好了，才开始分析。OK 啊，在没有讲好那个字眼下的话，讨论什么都没有意义的，其实。因为每个人都在想不同的东西。OK。我觉得这个可以先解决这个问题。等你把这个东西搞懂了，我觉得你后面的 explanation 会比较顺。不然的话，我前面都不懂，你后面一直讲，但是没 sense。所以你每一次一讨论一个东西啊，一个 concept， 一个词眼啊，先 define 好了先。比如说你要讲，你知道吗？你前面那个上有很多东西，知道吗？如果你要讲好来啊，其实有很多东西要讲。说一个东西是你自己要来 decide 哦，哪一个东西是人家一定要懂的，然后才可以懂的。有些东西可以把它掺起来一下，但是不是说你不可以你不可以不懂，不是说你可以不懂哦，你要懂。就是说先把它掺起来。因为我们暂时没有用到，我们把要用到的东西先把它讲清楚。
觉得我们这个 project 应该要这样子。
当然 ，OK， 这是一个正常 presentation 要做的事情。
OK，
所以你比如说你回去一个 slide， 你回去那个 Rutherford 的那个 slide， 其实这里面东西有很多字很恐怖，你知道吗？你明白吗？要 make sense of 这个 slide 啊，其实你要懂很多东西。
OK，
你又要懂 atomic nucleus，你又要懂 nuclear model，你又要懂什么叫做 orbital motion of planet。如果一个正常人不知道这东西的话，他是不知道你在讲的。
That be quite fun.
OK，
不是，I mean 就是说，like，我是说观众要懂，但是你自己更要懂，意思是说，
嗯
比如我在讲 Rutherford model 这个东西的时候，你后面应该有整个体系的东西在里面懂。
呀，
对，
就不会被提醒啊，老师刁难。
我去年
我还不够凶，我跟你讲啊，你如果去现实社会那种研究的人，你更够力。
呀，
对，
嗯
可能你一出一个新科研就刁你啊，虽然你可能是很对啊，可能你是对的，他们还是攻击你啊。
嗯
所以你要怎样能够站得住脚？你不能说啊，就是这样，就是这样，就是这样，没有人理你哦。你要知道，你的 paper 是被人 review 哦，不是你讲对是对哦，你要别人讲你对，你才是对的。我不是讲你要迎合他们啊，但是我的 point 是说，你要 convince 别人，明白吗？你要 convince 别人
，OK，
啊，你要去了解人家的问题是什么，其实。
了解，
了解的这样听。比如说我问你一个问题，你要了解一下我在问你什么，你才开始回答。
嗯，OK，嗯，maybe we'll go to second part first. Oh, the things I found lah, but I think I certain things that I'm not sure. So I put some question marks there. The first thing I not get it is the contravalent and covalent vectors. Is it introduced in the mathematics?
I think it's a different before the
The core definitions.
course sometimes physics term and math term to differ. So you need to bring the definitions up only within physics.
Okay. I didn't include the definition, but just how to use it. There's a maybe I try to call. I just try to read the book, the Hamilton book, the mathematical gauss theory that it said. This one, I just read it from yesterday was just mentioned it. One is that the Lie group is it the same as? I mean, is it as it in the math fields?
So legal is what it defines here.
It's defines it, but why define?
What do you think? Why chair like this? Why aren't this kind of no use? They define like this. I mean, why they consider it obviously is physics for this kind of things, so they consider it. But why define like this? Why chair like this? Why table like this? I need to ask this question. This question can answer. But why study this? Because something looks like this. There's something looks like this. Okay. So do you know what is already definition right now? You should know. So do you know?
The canonical structure of product is, what is the canonical structure of product? This one.
Just say that it's a product and
Or just a product.
okay, you can think of it as a product set. So like R cross R, R2 is a product of 2R. R cross R, R2 product set. Then the problem here is if you have a structure on G, okay, and then you can define a structure on G cross G. That's all. But it's not really important at this point. So the point you need to know is this D group is a group. And this group here is the mathematical term. So satisfies some axiom. Yeah, so basically group is a set. Okay, it's a set. And then set meaning there are elements inside there. Okay, and then this group has one, we call it a binary
Operations.
operation. Yes. So binary operation meaning you can combine two things, become one thing. Okay. So you can see here, G cross G goes to 0, combine two things, become one thing. And then there are some axioms you need to satisfy. For example, it is associative of this computation, this binary operation associative. So if you want to combine three things, you can combine the first two first or combine the last two. Still give you the same thing. And then group also has an identity element, meaning it's a thing that when you combine, you get it.
Do nothing.
Yes, do nothing. Okay, you can make it do nothing. Then the other thing is every G has an inverse. So meaning if you compose elements with an inverse, you go to the identity. Go back to identity. I think basically that's all. So, but here D group says that it's a group, so you can combine two things together. But at the same time, it's a manifold. So what is a manifold means here? So manifold is another big word in maths. So basically, how you think about it is locally meaning if you take an open ball, like what we say, the module, if you take an open ball around this any point, and then you can find that it actually looks like R and
Oh,
yeah, looks like the usual Euclidean space. Maybe you will ask me what looks like means in maths we'll say there's a map. There's a map from this ball to Rn such that it is bijection, and this need to be bijection, and then some structure need to be conserved. For example, we want this bijection to be continuous. Continuous is another word in Python. But most importantly here is saying that if you consider this as this is not binary, the usual binary operation. But usual binary operation is G dot H.
Yeah.
But here's G dot H equals. Okay, and then they require this map to be smooth. So this map meaning this map is differentiable, continuous at least. If you sit into the differential geometry, I think they should.
smooth. Yeah.
Yeah.
Yeah. Yeah.
Yeah, those are the terms there. Then you call this a different.
Smooth structure also is the smooth that we use.
Yeah. Yeah. So the smooth structure here actually refer to the local map. They call it a chart. The charts that you map local map to Rn. Those charts are smooth. Those maps are smooth actually. Not just continuous, but smooth also. But I don't think you need so many properties. The point here is you need to know that this D group is a group that is a manifold at the same time. That's all. I think. At least for now. I don't think you need all these details. Why you need to understand from this line. So this I'm teaching you how you read this line. So what you need to get out from this line here. You need to get out that D group is a group and manifold. That's all. Can you read again? See, this is the main point.
Read again, sorry.
Read again this line and then realize that this is the main point. 我现在在教你读重点，再读一次，看看这两个东西是不是重点。
因为它后面的都是会从里面衍生出来。
后面只是来辅助这个 manifold 的，呀，辅助这个 manifold，其实是 extra property 的啊。就是辅助的点
OK，
for 你啊，因为你应该后面的东西不会用到这个，有用到在读这个东西，应该有。但是你有没有读到那个重点呢？我的问题是，根本没有读到
还没有。
啊。
如果大概懂，大概大概。
没有，不是你要在不知道什么都不知道的情况下，你要知道 D group 是一个 group 和 manifold 读得出来。
OK，
啊，再跟你读。
Yes，
我现在在教你读书了啊。
对。
啊，不然的话你一定是读漏东西的，我跟你讲。
嗯。
再读一次，这两个是不是重点？
加不重点。
I mean，其他是如果你用到它就变重点，那反它是其他的点。至少你要读出 group 跟 manifold 的话，因为你连这两个都讲不出啊，刚才。
呀，
是不是？
呀。
啊。所以你现在 OK 了
OK，
不然再挖一个 definition 来读。
这是第一个 definition。好，还没到后面的失败。
不然哪一段你读不懂的东西，我们一起读啊。看我读出什么东西，看你读。
这一个。
OK， 可以。现在一点一看，解释什么叫懂我这个，直接读就直接解释。
直接解释。
Yes。我觉得这个是很好一堂课，很像刚才。
Topological group 是一个 group 的话，同时后也是 topological space 然后有这个以外。
就这样。哦。这样。
那后面的就没有OK。
I mean 你要用到的时候，你才要去 check 啊，你没有用到你就，它就是一个 group 的一个 space 就这样了。至于什么是 group，什么是 topological space，你就去找。
呀。OK。
所以你可以在不知道什么是 group， 不知道什么是 topological space 的情况下，讲出这个 topological group 是什么。你明白？然后人家再问你，what is a group？What is a topological space？ 再进去。
OK。
Instead of 你跟人家讲，这是 group 是 topological space。I mean 这个情况下，I mean 我们都会懂这些 concept 了，所以就是说，你介绍 group 这些这样的 topological space 在讲这个东西。但是有时候我们呢讲来，有个好像很多的就会乱，不是讲不可以啊，我没有讲不可以啊，只是说就是听众会乱，你要想到这个点。
OK。
没有讲不可以，但是你要知道听众是什么。
想太多，definition 太长的时候，
是
就是说你每次 present 的方式，就是说，假设我用你之前 present 的方式去 present 这个topological group 的 definition 呢，你会跟我讲 group 先，然后你跟我讲一大堆 group 的 property，然后你会再跟我讲 topological space，然后再跟我讲一大堆 topological space 的 property，然后再跟我讲这个东西，你明白吗？但是刚不明白，
不大就是没有解释那东西，可是先给他的东西，后面的东西啊，可是还没有对上前面那个要的东西。
你会先介绍介绍一大堆跟 group 相关的东西，你不只介绍 group 的 definition，你还会介绍 group 的 property，这个 make sense 吗？
哦，OK，
然后再介绍 topological space 跟 topological space 的 property。OK， 如果是新人啊，听完这些东西啊，已经是乱了，然后你再介绍 topological space，他们就不会进去了，他们就会进去了。OK， 但是你一进来说 topological group 就是一个 group 跟 topological space，他觉得很新奇。哦，原来这个东西是这两个东西，然后他就继续问什么？哦，这个第一个是什么呢？第二个是什么呢？
那在我的 presentation 要怎样？
改进 ，OK， 第一个要改进就是我刚才跟你讲的东西，把东西讲清楚一点。你看，假设你介绍这个东西啊，你一定又是整个东西跟我讲完，一个字没有骗。
OK，
所以刚才我叫你抓重点哦，先解释哦，这是 group， 这个就是 topological space， 但是哦，它还要同时符合这个条件。
OK，
因为你可以是 group 可以是 topological space， 但是可能不一定符合这个 definition， 对不对？如果不符合这个东西，只是我们不加 topological group， 要符合这个条件是，里面嘛，就有轻重，就是有轻重啊，就是有抓重点。
抓住。
这个其实也是 testing 哦，你对这个 knowledge 的理解来的。
对呀，
对。不然再讲一个 lemma 1.1.3。
连麦一点上。我会讲解释这个 lemma 1.1.3。 因为我会 test 解释的嘛，我会 test 解释的嘛。
读完对不对？
呀，
所以你看我怎样解释啊
OK，
So a group is a topological group， 这个没有什么好说短的，就是讲一个 group 是什么时候是 topological group， 当然之前已经define好了，其实你已经有个概念了啊，它一定要
the group， 然后同时候也是一个什么24，
这个乱的 topological space， OK， 然后它已经是 group 了嘛，所以你只要升 topological space 要讲了 ，OK， 所以它 if and only 发生什么事情 is a topological space， 喂，这样的话这两个条件都有了，还差别。
还差什么？topological space。
有啊，at the same time of topological space 啊，所以还差出。
下面的东西。
我去看看，你可以回去 check， definition。所以你看，你想东西的时候没有想回 definition 的，空想，这是错的。你不可以空想东西，有 definition 啊，上面有 definition。好，再去看，你看 GH 唱起来 ，GH 里边是一个 continuous， 你还要签这个东西。你刚不是讲全部都很重要吗？你现在又忘记这个了，这不是 contradiction 啊？你讲的话，对不对？你觉得很重要全部，但是你全部都忘记，对吧？明白吗？所以哦，你觉得全部很重要，但是你又全部记不起来，所以其实没有用。你要抓重点。哦，有 group，有 topological space，然后又要符合这个条件。你要把它想成一样重要也可以啦，随便你啦。但是我想告诉你的是，把这3个东西拆出来，不是一体的，它是拆的，
OK
拆出来，
OK
明白吗？是一个 group， 一个 topological space， 同时符合一个 map 是 continuous 的，把它拆出来，把东西把那个知识全部给它拆出来。OK， 明白吗？
I think so
明白吗？
Yeah
你知道我学生哦，我叫他们考试嘛，可以带7天，他们全部抄进去，然后他们考完试告诉我，老师没有用到7天，啊，没有懒用，周末没有懒用，他不知道他自己在抄什么东西，你明白吗？所以我叫你拆，把它拆出来。我也有一派学生不用器械的，考出来也是100分90分。怎么？他这东西已经在他脑里面了，拆出来啊！你看我拆出来，我现在当场拆。topological group 是什么？这个 group， 这个 topological space 符合一个 map， 什么 map？ 那个 map 是continuous的，什么 map 呢？一步一步这样慢慢进去哦。明白吗？如果每一个字都 equally important 在你的脑里面了，我不觉得有什么人的脑是可以记住这些东西的，明白吗？
Yeah
啊
OK
，OK， 所以你看 lemma 1.1.3跟这个的差别是什么？它把那个 GH 的拆成2个 map。你看他在讨论 G cross G 去 G 的那个 map 是 combination 吧？上面是有 inverse 在 ，then how to compensate 有这个 H inverse， 它 define 另外一个 map 叫 inversion， 它也要求这个 inversion 是 continuous。So now instead of asking for one map to be continuous， 它 ask for 2 maps to be continuous。And then the result of this lemma 是说 these 2 conditions are equivalent。还不错哈。
Yeah
你回去想一下我讲的东西，回去再读一下。
OK
我没有 expect 你当场讲出来，但你要理解 ，OK 吗？
OK
啊，
Thank you ，I'm not sure this one still need to be bring out because Lorentz transformation we'll use it in we'll use it in the QFT, but I don't fully understand on this context this context there. Yeah. First I bring out the idea that I know. Okay.
哦，不懂你在讲话。
I bring out the idea that I understand from the books. Okay. Okay. The Lorentz transformation comes from Einstein principle of relativity. If come with the it come with the come with the assumption that the law of nature takes the same form in every inertial frame of reference. Inertial frame of reference is not the frame of reference is not accelerating. Okay, so it's a inertial frame of reference. Okay, so the Lorentz transformation here is I think you want to conserve something. What is something? Lorentz transformation, let's say we have this frame of reference, this set of coordinates for four coordinates, including the time dimension. So it's CT, X, Y, Z, where C is the speed of light. When I want to transform into another inertial frame of reference, we can do the transformation because a Lorentz transformation, and it is conserved of what is called the delta X here. The space-time interval between the two events. Yeah, and also the formulas, the transformation comes from the assumption of the speed of light is constant. So we'll get and also it throw away the absolute of the times, which when we think of the frame of reference, it should have a same when the event occur, it should have the same time in two different frames. So whereas in the this new frame of reference, the time between the events can be the time interval can be different for two frame of reference. And also some of the indices that not sure. Yeah, some of the indices that yeah.
That time, that's all.
Thinking how we can bring out the discussion. I mean how we can. Maybe the second part is the things that I don't know how do I bring out in a proper way. I mean, because I'm not sure, although I'm not confident about from what I'm talking. So
Why the, why you write this thing?
yeah, try work on it. Try and okay. Okay.
And like you have seen in my class, right?
Hmm.
Everything we introduce in the class, right, must be used through some important theorem analogy. So I use the theorem to construct what definition. So you have to come back to a question is what you want to achieve. So where do you need Lorentz transformation for? And then how you use the Lorentz transformation. Then you need to introduce how Lorentz transformation works that way. Then later when you use it, because Lorentz transformation can do this, so we can use it better. You understand?
I'm not sure, because I'm not sure the part that afterwards will I use it? Because I mean, we have the endpoints of, we have the M's for endpoint, but I'm not sure all the ways, along the ways, what the tools we need. This I think it's the problem that I'm facing now.
So I think the problem why you're facing is you don't quite know your goal yet. If you know your goal, surely you know what you do. Because your goal is not abstract, it's not worked out yet, it's already being worked out. For example, I give you an example. So go back to the topological group again. Let's say I want to reach to this definition. What do I need to do?
What do I need to do?
How do you do?
Understand what is a what is a group, what is a topological space.
Yeah. So if you already know your goal well, for sure you know what to do.
Okay.
Simple idea.
Hmm.
You don't know your goal well yet. You only know a broad idea. Another thing is don't try to squeeze too much idea into one topic. You need to make sure you expand one idea freely. So my advice is to define the word properly first. Only then we can discuss problem. Otherwise, we don't know what's the thing we're discussing.
Okay.
Yeah. So next time, be aware, whenever you throw a new word, make sure we all know what that word means. First. Yeah. We don't rush to explain what's the consequence. Too rush already. 太紧张了。
Okay. So let's stop.